Welcome back, folks. In today's class, I'm going to talk about the concept of force, and with that, I will also take some of the problems from chapter 3.1. Specifically, I'm going to take an example which is 3.4. Okay, so I'm going to talk about the force. So force has two formulas. First one is force equal to mass times acceleration. Another formula is also, which is force is the sum of the remaining forces, whatever forces which are acting on a particular object. So if this is an object, uh, and then these are the forces which are acting on this object. So if I take the sum of all these forces, whatever that force will come out to be, that will be the net force. So this is the formula for net force. Now this net force, whenever we talk about this, is a net average force. So I'm going to call it as average. Also keep this at the back of your mind, because you will need this later on. So now if I take an example of this box, and in this box, if this is a force which is acting towards the east direction, let's say this is 10 Newton, and there is a force which is acting in the opposite direction, which is 20 Newton. So I'm going to ask you a simple question: in which direction this object is going to move? And you're going to say this object is going to move in towards the left direction, and that will be the net force on this object. So F net will be equal to F1. I'm going to call this one as F1 and this one as F2. So this will be F1 plus F2, and so this will be 10 to the right, and this is 20, which is to the left hand side. So I'm going to mark this one as negative force. Same, I'm using the concept of vector from chapter 2.2. That's the concept I'm using. So the net force will come out to be equal to negative 10 Newton. That is the net force. And net force, if I wanted to simplify it furthermore, net force is also equal to ma. That's the formula which I wrote at the beginning. So that's the formula. I'm going to write it here. This is equal to negative 10 Newton. And now I wanted to find out, let's say I wanted to find out acceleration, and the mass of this box is 5 kg. So how much is the acceleration for this box? So I'm going to write it as 5 times a, which is equal to negative 10 Newton, and dividing both sides by 5. And then acceleration will come out to be negative 2 Newton per kg, or I can also call it as kg meters per second square. Both mean one and the same thing. So this units I've derived it from here, because the unit of force is Newton and divided by mass, which is kg, and these are the old units which you can recall from chapter 1. All right, so this was the basic about the force, net force. Now if let's say this object is not moving, and if the object is not moving, then net force value will be equal to 0. Why? Because acceleration is 0. So let's say there is a certain force which is acting on this direction, and there is another force which is acting in this direction. Now I'm going to make these forces equal. If I'm going to make them unequal, then object has to move. So because I've taken that kind of a question in which I have to take the forces equal, so I'll put this as 10 Newton, this as 10 Newton. So I'm going to try and find out the net force on the system. Net force will be equal to F1. I'll call this again as F1, this one as F2. So F1 plus F2 will be equal to how much? Negative positive 10 minus 10. Well, I should place it like this. So this is equal to 0. Net force is ma, mass times acceleration. So acceleration value will come out to be 0 meters per second square. So what I'm trying to say here is, if the object is not moving, means if the object is stationary, net force on the object will be equal to 0 always. So if in a question given to you that object is not moving, remember this thing, you'll put the net force equal to 0. Now this is the concept which I'm going to use in the next problem. So I'm taking an example 3.4 from the Pearson book, and it is on page 134. So the example is like this, that there is a signboard which is hanging from the walls, and with the help of strings, and this signboard, this welcome signboard has a mass of or not, the mass is not given to it, is exerting a force in the downward direction as 245 Newton. That much force this is applying in the downward direction. Now I wanted to find out what is the tension in this spring. So Ft1 I'm going to call it as, and I'm going to call this one as Ft2. These are the two values I'm going to try and find out. So force in this rope and force in the other rope. Whenever we specifically talk about rope, so we call it as tension. That's why I marked it as T1 and T2. These are the two values which I wanted to calculate. And one more thing given to me, that this welcome signboard is stationary because this is hanging. So I want to, as I said, I wanted to find these two values. So how can I find this? So I can clearly see this is a two-dimensional problem. So this is somewhere in the northwest and this is somewhere in the east direction. So I have to segregate a two-dimension problem into two one-dimensional problems. So I'm going to write the formula in x direction first of all for net force. X direction. So F net in x direction will be equal to F1. How many forces which are acting in the x direction? Let's see. So this force Ft2 is acting in the x direction. So I'm going to call it as Ft2, which is acting in the positive direction. So I'll call it as positive force. And is there any other force which is acting in the x direction? Yes, there is one, which is the component of Ft1. This component. So if this is the actual force, this is the force, and the component in x direction will be Ft1 cos of angle theta. And the angle given to me in this question is down here. This is theta equal to 55 degree. If this angle is 55 degree, this angle will also be 55 degree. We can complete the geometry here. So this becomes a right angle triangle. These two angles are same. So I'm going to call it as Ft1 cos of 55 degree. And this is acting towards the left hand side. So this is a negative force. So I'm going to represent it here plus minus Ft1 cos of 55 degrees. Now net force Ft2 value, Ft2, I'll write it as it is, minus Ft1 cos of 55 degrees. How much is the net force if the object is not moving? This value will be equal to 0. Then I'm going to move this on the other side. That's going to become Ft1 cos of 55 degree equal to Ft2. Now notice I cannot solve it further because I don't know Ft1, neither I know the Ft2 value. So I'm stuck here. So what I'm going to do is, to solve this question, I'm going to move towards the y direction, like you guys used to do in the projectile motion. If you cannot solve in one direction, you try and solve it in the other direction. So I will write it y direction. So F net in y direction will be equal to, how many forces are acting in the y direction? If I see, one component of Ft1 in the upward direction and the other force is downward, which is 245 Newton. So Ft1, it is a positive value, sine of 55 degrees minus 245. And net force, because this sign is not moving in any direction, so net force is equal to 0, equal to Ft1 sine of 55 minus 245. This is going to go on the other side. 245 equal to Ft1 sine of 55 degrees. Now dividing both sides by sine 55. So if I divide this by sine 55 degrees, so this value going to come approximately equal to 299. So Ft1 is 299 Newton. So here I'm going to talk about one more concept. if you see carefully, I figured out the value of ft1 here. I started with ft1 sine of 55. Usually what students do is they think this value is 299. This value cannot be 299 because if this is 245, opposite force has to be 245 to balance these two forces. If this is 299 and this is 245, then the object will start moving in the upward direction. So this is ft1. This component was ft1 sine of 55. That's what it was. See here, this value, which is still equal to 245. The value which we figured out for ft1 is this value. This is ft1. This value we figured out. This value. This is 299. And the component of that in the vertical direction is 245. So hopefully you are clear about that. So we figured out ft1 here. Now this value I'm going to put back in this equation. So 299 cos of 55 degrees will give me ft2, and that's going to be approximately equal to, I think that's going to come out to be 172 Newton. Make sure your calculators are in degree mode. And we figured out both the values ft2 and ft1 from this question. Hopefully you were able to understand this question. So I'll highly encourage you to solve the practice problem with that. And one more example here. I'm not going to solve this fully, but I'm going to give you a hint for this question. Question number 7 on the check and reflect for 3.1. It is on page 136 on my book. You check it on your books also. I hope it is page 136. So this is the question. So there is again a welcome sign which is hanging from here, but now the arrangement is a little different. This angle given to me is theta equal to 55 degrees. This angle again given to me is 55 degrees. So these two angles are given to me, and I wanted to find out ft1, ft1 and ft2 values. Now, how I'm going to solve this? Again, this is 245 in the downward direction, newtons. So again, I'll write the equation in x direction and y direction first of all. So x component will be this one for ft1, and x component for ft2 will be this one. So this angle is theta, this angle is theta. Again, the theta angle is 55 here, 55 degree here, because this is 55, so this is 55, this is 55, so this will be 55 degrees. Now I'll write down x direction, f net in x direction. So that will be equal to f net equal to ft1 cos of 55 negative, because this is going to become a cos component. Again, if someone is having confusion, this is how we are doing it. So I'm going to complete a right angle triangle here. So that's how this becomes the cos component. Same thing I'm doing here. This is imaginary line, the green line which I'm drawing, and this one will be again the cos component for ft2. So plus ft2 cos of 55 degrees. Neither I know the ft1, neither I know the ft2 value, but net force is 0 because this is not moving in x direction or y direction also. So I've marked it 0 because the object is not moving in x direction. So, and we are taking everything in x direction. So this is going to go on the other side. ft1 cos of 55, ft2 cos of 55 here. And then I can cancel the cos 55 on both sides. ft1 equal to ft2. So from here, I've been able to figure out that these two forces are equal. Although I haven't been able to figure out the value, but I've been able to figure out that they are equal. Now I'm going to try and solve this in the y direction. Y direction. So f net is equal to ft1 sine of 55. This is positive because this is acting in the upward direction. So this is how it's going to be. This is ft1 sine 55 degrees from here. So you can call from here also ft1 sine 55 degrees. And that same thing, this is ft2 sine 55 degrees. I can show it here also, ft2 sine 55 degrees. Now both are upward, so positive, plus ft2 sine 55 degrees, and now net force is 0. And now because I know ft1 and ft2 are equal, so I can replace ft1 with ft2, or you can replace ft2 with ft1, whatever you want to do. So ft2 sine 55 plus ft2 sine 55 degrees. That's how I'm going to write it. One I forgot to write, 245, which is acting in the downward direction. Here, 245 acting downward. And this 245 will gonna go on the other side. I can write it here, 245 equal to this. All right. So now this, remember the concept, x plus x is what? 2x. So ft2 plus ft2 sine means same value. If I add them, this will be 2ft2 sine 55 degrees equal to 245. Now dividing both sides by 2, and then ft2 sine 55 degrees. So I think half will be 132. Well, you can 122.5. Now dividing both sides by sine 55. I will leave the answer for you guys to figure out. I think it should come out to be approximately 149.5 or 150 approximately. You can finish this question. So hopefully you were able to understand this question, and I'll see you with another lecture video. Till then, goodbye.